Hello everyone, myself Dr. Pinaki Acharjya, Professor, Department of Computer Science and Engineering. Today I will discuss on the concept of process. So basically in our previous classes we have discussed on the various introductory sections of the operating system, and in this class we will discuss on the processes. So actually what happens that an operating system, we know that it executes a variety of programs like batch systems where the jobs are executed one by one. All the jobs are allotted in a batch and one by one all the batches are executed and the job is successfully executed, we can say. And we have our timeshare systems where user programs or tasks are there, where one by one all the user program or the tasks that we have are executed sequentially and the entire execution is done. Now whenever we discuss on the processes, so throughout our syllabus basically the job and the processes, these two terms are interchangeable. Means we need to understand whenever we will discuss on the processes, and if sometimes the job, this particular terminology comes, at that time we have to understand that we are discussing on the processes, and vice versa. Whenever processes will be discussed and the job comes, so we will understand that we are discussing on the processes. So for both job and processes basically it denotes the same phenomena. Now what we can say about the processes? Basically whenever a program is in execution, at that time we say that it is a process. So the programs basically resides in the secondary memory devices for their entire lifetime until and unless we are executing them. So whenever we are executing the programs, at that time the programs are fetched from the secondary memory devices to the primary memory device, and from the primary memory devices their execution is basically done. So in a simple manner we can say that a program is in execution is called process, and this execution is done in sequential fashion. So basically we have the programs where we can say the programs are the set of instructions. So whenever all this set of instructions are executed in a sequential fashion, at that time we can say that the process execution is going on. Now whenever this particular process we discuss, at that time we need to know that in a process basically a program counter is there, stack is there, data section is there, and the heap is there. So basically heap is responsible for memory that is dynamically allocated for the particular process. Suppose if one new particular process, a new process is created, at that time the heap will be there with the process and it will denote that memory that is dynamically allocated for that particular process. Now after that we have the program counter, where in the program counter basically it indicates the next instruction of the process. Then the stack is there where all the temporary data are stored in the stack, and the data section is there where the global variables are basically stored. So after that whenever we will discuss about the processes, at that time we need to understand one particular concept, that processes are active or dynamic entity. In vice versa the programs are static entities. Now as we are saying the processes are active or dynamic entity, at that time it is a must that behind this dynamic concept the changes of the process states are there. Processes changes their states throughout their lifetime. So basically whenever we discuss about the process states, at that time we need to know that there are 5 states of each and every processes: new, running, waiting, ready, and terminated. So one by one I will discuss all this. Suppose first a new process is created, at that time we will say it is the new state of a particular process. Suppose one particular process is created, at that time the first state of that particular process will be the new state. Second state that we have is the running state. It means that all the instructions are being executed in a sequential manner. Instructions are being executed. It is the running state. Third, we have the waiting state. In the waiting state, we can say the process is waiting for some event to occur. It means suppose one particular process is in running state. It means all the instructions are being executed with the help of a processor. Now, what happens? Suppose sometimes the processes needs some input output devices to complete their execution. We need to remember one thing, that basically there are IO based processes and CPU bound processes. IO bound processes and CPU bound processes. IO bound processes spends their entire life in execution of IO operations, and the CPU bound processes spends their entire life doing the computational things, computational processes. Now suppose one particular process arrives, it is in the running state, and at certain moment it needs one input output device to complete its execution. At that time, it may be the case that that particular input output device which is required by that particular process is busy with some other processes. At that time, obviously that particular process will move into a waiting state, and it will wait in a waiting queue until and unless it gets that particular input output device. Whenever that particular input output device will be acquired by that particular process, it will again move to the running state and it will start its execution, further execution. So this is the third state that we have, that the waiting state. Now after that we have the ready state, where the process is waiting to assign to a processor, and the fifth state that we have, that is the terminated. Whenever the process has finished its execution, at that time we can say that it is the terminated state. So first a new state will be there. If I go sequentially, first the new state, then the process is being created, then second the ready state, the process is waiting to be assigned in a processor, third running state, instructions are being executed, fourth waiting state, the process is waiting for some event to occur, and fifth the terminated, the process has finished its execution. So as a particular process during its execution or during its lifetime, it moves through this all 5 states. This is the reason we used to say that the processes are active or dynamic entity, and as the programs resides in the secondary memory, until and unless we are executing them, so the programs are static entities. Now after that, this is the diagram of a process state. As we have discussed the 5 process states so far, so let us discuss more thoroughly with this particular diagram. This is the process state diagram that we have. As you can see, we have a new state, a ready state, a running state, a terminated state, and a waiting state. So all these 5 states we have discussed so far. Now first the new state, whenever a new process will be created, at that time it is the new state of that particular process. After that, what happens? After that, that particular new state, whenever the process will be in the new state, it will be admitted to the ready state, where in the ready state that particular process will wait until and unless it is turn in the processor. So the process is ready and it is waiting for its turn in the processor. This is the ready state. After that, we have the running state. As you can see, and one particular arrow is from the ready to running. It means the processes move to the processor and they are in execution. So this is the third state of the processes, the running state. From the running, if a particular process successfully executes, at that time it is the terminated state. So one particular arrow is there from the running to terminated. Now As we have discussed also, that it may be the case that for some processes some input output devices are needed. So far we have discussed about the input output devices. It may be the another case that with the input output devices, or it may be that some IO or event completion is also needed. So in these cases, from the running state, if any IO is needed at that time, that particular process will move to the waiting state. From the running state, it will move to the waiting state until and unless it gets its IO. Whenever that IO event will be completed, at that time, that particular process again it will move to the ready state. From the waiting state, it will move to the ready state, and obviously at that time that particular has its particular IO, and from the ready again it will move to the running state and it will start executing, and obviously if it successfully completes, it will be terminated, it will move to the terminated state. And if any other input output device is needed, that time it will again move to the waiting state, then from the waiting state it will get its IO, it will move to the ready and then running again. So like this the execution will go on. It might be the case that from the running state, suppose some interrupt occurs. Whenever any interrupt will occur, at that time the processes will move from the running state to the ready state directly, and after completion of the interrupt, that from the ready state it will move to the running state and it will execute. Whenever it will be executed successfully, the terminator will be there. So from the running to terminate, that exit means it successfully completed its execution and it is terminated from the system. So this process state diagram we have. After that, we need to know, so whenever all these process states are there and the processes moves from one state to another state, at that time we need to understand that each and every process stores their present information in a block which is called the process control block, PCB, or task control block, TCB. Process control block and task control block, this is interchangeable. So whenever each and every process moves from one state to another state, it saves its present status, its present information in a block which is called the process control block. So what are the different informations basically a particular process stores whenever they changes from one state to another state? Here, as the list is there, you can see the process state, first, second, program counter, CPU registers, CPU scheduling information, memory management information, accounting information, IO status information. All these informations are being stored in a block which is called the process control block. As you can see in this diagram, more information you can understand when the pointer will be there, process state will be there, process number will be there, program counter will be there, registers will be there, memory leads, list of open files, and so on. So at a glance we can understand that whenever the processes moves from one state to another state, they need to save their entire information and then it will move to the next state, and again whenever from the next state to third state, it will again save their all the informations. So these are the different informations that a particular process stores: process state, program counter, CPU register, CPU scheduling information, memory management information, accounting information, IO status information, registers, memory limits, list of open files. All these informations are being stored by the particular process in its PCB. Now after that, this is a very interesting diagram that we have, interesting concept, the CPU switch from process to process. What happens, as we have discussed, that it may be the case that one particular process moves from the running state to the waiting state because some IOs are needed. So at that moment, what will happen? The CPU will be idle? No, it is never. CPU can't be idle. We have to utilize our CPU as much as possible. So in this case, whenever one process will move from one running state to the waiting state, at that time in some other processes will be in the CPU, in the processor, and they will be executed. So this particular concept we can discuss with this particular diagram, where as you can see here process P0 is there and process P1 is there, right? Now P0 starts its execution. Okay, so P1 starts its execution first, then what will happen? P1 P0 will start its execution. P0 will start its execution. So first P0 will save its PCB. Then what will happen? Suppose PCB 0 is the PCB of process P0. Suppose P0 needs one input output device, so it will move to the waiting state. So at that time what will happen? It will save its PCB. So that PCB 0 is there, and whenever it moves to the waiting state, so any other process which is in the ready state, it means we can understand that process P1, suppose it is in the ready state. So process P1 will be in the processor. So reload the state from PCB1. PCB1 is with the P1. So PCB1 will be reloaded. PCB1 is the PCB of P1. So it will be reloaded and PCB1 will start its execution. So suppose PCB1 is in execution. It might be the case that some interrupt or system call it is generated, IO event, the process P0 gets its IO. So process P0 will start its execution again. So at that time what will happen? The process P1 will be moved from the processor to the waiting state and the P0 will start its execution. So like this entire execution goes on. So whenever one particular process moves from one state to another state, suppose from running to waiting, so another process will be there in the processor and it will start its execution. Suppose the first process gets its IO, it will come into the running state again and the previous process will be moved from the processor to the waiting state. So like this particular discussion can be done with this particular diagram, the CPU switch from process to process. After that, whenever the process scheduling is there, at that time we need to understand that the processes moves from one state to another state. It means processes moves from one queue to another queue. Suppose the job queue is there, which the set of all processes in the system. The ready queue, the set of all processes residing in main memory and ready for their execution. Device queues, the set of processes waiting waiting for an IO devices, and the process migration is in between the various queues. So job queue is there, ready queue is there, device queue is there. So all these queues are responsible of switching of the different processes from their different states. Now, this is the process scheduling representation. Suppose one particular process arrives in the ready queue. From the ready queue, it moves to the CPU for its execution, and suppose that particular process do not need any input output devices for its completion. Suppose it is a pure CPU bound process. So directly ready queue to CPU, from CPU to terminate. Now suppose some IO bound processes comes. At that time what will happen? The second condition, ready queue to CPU. Then from the CPU it will move to the different other conditions, like IO request is given, then it will move in the IO queue. IO queue means the waiting state. Whenever the IO will be acquired, it will come in the ready queue, and from the ready queue to the CPU, and it will be executed. Another case, time slice expires. In the time sharing systems, obviously all the processes are given a fixed time for their completion, for completion or for their execution. Suppose 5 processes are there, it may be the case that 5 milliseconds is given for those processes. One process will execute for 5 milliseconds, then another process will come. That process will execute for 5 milliseconds, another process will come. So like that. So suppose for a particular process, the time slice expires. At that time what will happen? It will be moved in the waiting queue again, and from the waiting queue it will move to the ready queue and from the CPU. Suppose to complete a execution of a particular process, a child process is also needed. So first it will fork a child, it will create a child process, then child will be executed, and then it will be moved to the ready queue and to the CPU like this. Wait for an interrupt. Suppose one interrupt is needed, interrupt is generated. So wait for an interrupt. Whenever the interrupt will occur, it will be in waiting state. Whenever the interrupt will be overcome, at that time it will move in the ready queue, and from the ready queue to CPU, and like this the execution is going on. So this is the process scheduling representation of the process executions that we have. Then we have the schedulers. Schedulers are also very important in the process scheduling, in process execution. we have long-term scheduler, short-term scheduler, and mid-term scheduler also. So the long-term scheduler or job scheduler basically selects the processes which should be brought into the ready queue, and short-term scheduler selects the processes which should be executed next and allocates CPU. So from the job pool, from an entire job pool, suppose the secondary memory, what happens, the long-term scheduler pulls those appropriate processes which should be there in the memory for their execution. So from the job pool to memory, it is the job of long-term scheduler, and the job of short-term scheduler, obviously from the memory to dispatch them into the CPU. So this is the role of short-term scheduler that we have. Also, the short-term scheduler is evoked very frequently, as from the memory they dispatch all the processes, all the instructions to the CPU. Long-term scheduler is evoked very infrequently, as from a huge job pool it fetches the appropriate processes to the memory, so a little time is needed. So it is the case, we say the long-term scheduler is maybe is a little bit slow, and short-term scheduler is very fast. Short-term schedulers executes within a milliseconds, and short-term scheduler and long-term schedulers may need seconds or minutes to do their particular task. Now also it's a phenomenon that the long-term scheduler controls the degree of multiprogramming. What is the degree of multiprogramming? Degree of multiprogramming says there must be a good combination of CPU bound processes and IO bound processes into the processor. As if this mixture is not there, a good mixture is not there at that time, suppose if only IO bound processes comes, our input output devices will be busy and the processor will be idle, and if only CPU bound processes comes, our CPU will be always busy and our input output devices will be idle. So a good degree of multiprogramming, a good mixture of IO bound and CPU bound processes are needed in the processor, obviously. So IO bound processes spends more time doing IO than computations, and CPU bound processes spends more time doing computations only. So this is the IO bound and CPU bound processes where the good mixture of degree of multiprogramming is needed, and the long-term scheduler basically maintains this degree of multiprogramming as it fetches the appropriate instructions from the secondary memory device, from the huge job pool to the memory. So here for the degree of multiprogramming, basically the long-term schedulers are very much responsible. Now after that, the addition of medium-term scheduling, the mid-term scheduler, obviously. So mid-term scheduler is responsible for swap in and swap out of the processes in the CPU. As here you can see that from the CPU a swap out is there, so the partially executed processes are swapped out. It means suppose one particular process is in execution and a higher priority process arrives, so the higher priority process should be there in the processor for its execution. So suppose one higher priority process comes, so the present process will be swapped out. We are saying partially executed processes, and what will happen from the ready queue, that higher priority process will be in execution. It's just an example of the higher priority process I am giving you with the higher priority process. So from the ready queue it will move to the CPU for that particular process. If any, for the particular high priority process, if any input output device is required, it will move in the waiting queue for its IO. Until it gets its IO, it cannot come into the CPU for its execution. So what will happen? In between, the previous partially executed process will be swept in through the ready queue to the CPU, and it will be executed. And whenever the higher priority process will get its input output device, again it will move in the ready queue, from ready queue to CPU, and it will be executed. So this is the role of the mid-term scheduler that we have. So this long-term scheduler, mid-term scheduler, short-term scheduler, all these are very important in the process execution and in process scheduling, right? Okay, so throughout this particular class, what we have learned, if we take a quick recapitulation, that processes are there. Processes means programming execution are called processes. Processes are active or dynamic entity, as they changes their states during their lifetime. 5 states are there with the processes: new, ready, waiting, running, terminate. After that, obviously, all these particular processes, what happens? Process scheduling, schedulers are also there: long term scheduler, mid term scheduler, and short term scheduler, right? So for today, this much discussion I think is enough. After in our next class, we will discuss further on this process management chapter. So for today, uh, thank you, and hope we will meet in the next class. Bye.